And we are started. Okay. Yes, Zoom, I know. No, the meeting's already started. What are you talking about? Oh, Zoom, don't be a... Okay, anyway. Hi! I think we're on use. Yes, I see the YouTube stream going now. Hey, everybody. My name is Smitty, N6MTS. I am here today with Ben KN4RFT and my very grumpy cat. Oh, my gosh. Say hi, Ben.
Hello, everyone. I'm Ben KN4RFT.
And, oh, I got the cursor right in the middle of his screen. Ben is a listener of the Ham Radio Workbench podcast, and he reached out to me on Discord and started asking me some questions about an analog mixer that he built and designed. And I started asking some more questions about it, and I just was so impressed with the project that I wanted to present it. And then he also mentioned, and I've got this other weird side effect problem that I want to understand, and I knew exactly what the problem was and how to fix it. And so I talked him into coming onto a live stream that's going to be kind of two parts. One is giving him an opportunity to show off this awesome project he's built and to talk about the problem that it was designed to solve, and how he went about the design and build and all that fun stuff. And then after that, we're going to talk about the problem that he's having with it and how to go about fixing and addressing that particular problem. So let's just get started. But before we do, actually, I want to say hello to the chat room. We have Steve. We are live. Yes, we are, Steve. We're actually going to wait like another minute or two, I think, before we get started too much, since I did click the go live button a bit early. But looks like we got 5 viewers. Fix it with his... I'm going to need more OHIS. No, this is not an OHIS discussion. This is a analog audio design discussion, which might help people when they're designing OHIS devices. I will leave that as an exercise to the reader. But no, this is not a sales pitch or a standards advocacy presentation. So, cool. First off, Ben, why don't you tell us a little bit about yourself and what your background is and how you came to ham radio? And you're muted. It's got to happen at least once in every stream.
Feel like I'm at work now. Thanks, Mark. My name's Ben. I'm KN4RFT. I've been a licensed amateur radio operator for going on 5 years now. And really, I was looking for a hobby when I came into amateur radio. It was either going to be radio or beekeeping. And yeah, I'm an engineer by trade, so amateur radio was a good fit and has been probably the most rewarding technical hobby I've had. So in that time that I've been licensed, I've upgraded to extra, and I do some operating from home, but since I work from home all the time, I have primarily moved to portable operating and parks on the air.
Just getting out of the house.
Mm-hmm.
Yeah. You should try making ham radio your job and see how much you do it as a hobby anymore. Excuse me. Very cool. How'd you get into ham radio?
I was kind of in the preparedness mindset when I was looking at hobbies, and I was thinking, ham radio would be cool. We had an event in the Raleigh, North Carolina area maybe 10 years ago where one of the main fiber optic trunks for the area's cell phone communication was cut, and just no cell phone coverage for like 6-8 hours. Didn't really know what was going on until I heard about it on the news, but I knew I couldn't make any calls. And with that kind of in the back of my mind, I was thinking, wouldn't it be nice if I wasn't dependent on any kind of infrastructure for communications?
And hence, you found amateur radio. That sounds about right. All right, very cool. You prepared some slides. Do you want to share your screen and dive into those slides, or do you want to do this some other way?
That would be great. And yeah, the slides will help me kind of illustrate my points as I kind of give an introduction on my project.
Sounds good. Go ahead and just start your screen share whenever you're ready. There we go. Oh, nope. Just kidding. Stand by. No. What the heck? Standard view. Oh, I just need you to get out of full screen. Exit full screen. There we go. That, I think, is showing up correctly. Okay. You are sharing your entire screen right now.
What? Oh, dear. Thought I was just sharing one screen. Give me 1 sec. Let's just do the PowerPoint.
And will you stop going
How's
full
that?
screen? Perfect. Yes, exactly.
Okay.
It's almost like we're pros at this. Almost.
Almost like we should be.
Almost.
So at the end of 2019, going into early 2020, I found myself working from home full time instead of commuting to an office, which allowed me a little more freedom on my audio preferences during the day. I wasn't the only one working from home. My wife was as well. So I wanted to minimize the impact of what I was listening to on her. In this time, I found myself using 2 or more pairs of earbuds to listen to content on my computer, my cell phone, the local VHF repeaters, and eventually on HF, outside of working hours. And I had 3 to 4 devices that I was juggling audio feeds from. After some searching, I learned about audio mixers and started exploring consumer grade solutions. Let's see, make sure I can advance through these slides. So this was what I arrived on for a off-the-shelf solution. The MakerHeart Just Mixer 5 allowed me 3 audio inputs and 2 outputs. Worked pretty well, but I really wanted to have 4 inputs so I could cover at the time my Flex 3000, my ICOM 7100, my cell phone, and my PC, and be able to push that to either a set of headphones or a set of powered speakers on my desk.
I will point out that no matter how big your mixer is, you'll always need at least 1 more channel. That's just from personal experience. That will always be the case. Anyway, proceed.
I'm going to get to that, actually. From there, I investigated some home-built solutions and followed a walkthrough on building a line-level audio mixer from Bob Heil. I believe that was on Ham Nation episode 164, if anybody's interested. This handled mono audio and was pretty easily adaptable to a stereo solution by changing the potentiometers there. I also found a video on the, I believe it's Matt Sub YouTube channel that covered building a 5-channel passive audio mixer with stereo pots. Back in April of 2021, I even reached out to Smitty one time. Smitty, you might not remember this, but we talked on the thing that used to be called Twitter, and you were a great help, but a lot of it went over my head since I don't have a lot of experience in audio.
Well, okay. Yeah, sorry. Twitter's not exactly the right forum for doing long-form technical help either, so...
No, absolutely wasn't, but I did appreciate you trying to educate a young ham radio operator.
Well, glad I could help.
One downside I found with the passive audio mixing was I found myself getting ground loops a lot, and I ended up having to buy a lot of these little ground loop isolators for each line coming into the mixer. I think this is actually it. What brought me into the conversation where Smitty and I started talking about audio mixers. So this was my first attempt to add an audio mixer. This was back in 2021. I wanted 5 channels, which would be one more than everything I was trying to get right then. And I wanted 2 outputs in order to be able to power both headphones and a set of powered speakers on my desk. So this was rough, I'll admit it, but it worked, and I was pretty happy with the results. At this time, I didn't have...
It's brilliant is what it is, by the way. I love the use of the what looks like a heat shrink, the separator case that your heat shrink came in. That is brilliant. That is a brilliant reuse of materials, and this is what I had laying around, and that I just love it. I love everything about this.
Well, I appreciate it, and you hit the nail on the head. It was something I had laying around, and it fit the need.
Yeah.
I was able to clean it up a little bit on the second revision. In that same time, I purchased a 3D printer, and my main focus for work is 3D modeling and solid modeling, so I was able to work up something pretty usable in FreeCAD to run off on the 3D printer.
You and I need to talk afterwards. I didn't realize that's what you did for a living. I'll talk to you after this.
Yeah, absolutely. On the version 2, some of my goals, I'd never done any through-hole soldering, so I wanted to use through-hole components, wanted to actually use prototype boards on this one, and wanted it to be a little bit cleaner. We still have 5 inputs, 2 outputs. I've been pretty happy with this. I thought I was going to build some audio isolator transformers into the circuits and eliminate those ground loop isolators. Unfortunately, I've still needed the ground loop isolators on this, so I'm wondering if there's some magic I've missed. I've got a couple of slides just on the rough layout for that mixer. Again, I haven't done a lot of through-hole soldering, so I wanted to lay it out before I made a mistake. And yeah, it did run over onto 2 pages for me, but that mixer's worked great. I've been very happy with it, except for sometimes when I turn off my Flex 6400, I can hear the audio coming from the mixer through the front speaker on the radio. Yep. So I'm thinking there's some kind of back feed, and I'm hoping there's a way to alleviate that as well.
There is. Yep, we'll be talking about that later.
Just in case anybody wanted a quick summary, here's kind of the audio chain for my desk: 2 radios, PC, an old cell phone, because we all have those laying around now. And I actually do send all of my audio to a Bluetooth transmitter, so I'm able to use Bluetooth headphones around the house at my desk, not feel like I've got wires linking me to anything. And for both of my amateur radios here at the desk, I have boom mics, so I'm not tied to anything either. And let's see, I just had an additional slide on the transformers, but I think we're going to talk about those. Smitty, if it's all right with you, I'll stop sharing and turn it over to you.
It sounds good. Oops, we'll just do that. Oh, no, got to put you back into that view. There we go. Whew. All right. That's kind of a weird interaction between Zoom and OBS here, so we got to make sure that everything's in the same modes as we do this. Yeah, so I love what you did where you identified I won't say a problem, but a need. You're like, I want a device that does X, and X in your case was take the audio from all of these devices, mix it together, and send it up to my headphones and off to powered speakers. So you're not swapping cables around or having to use the crummy speakers that are on the devices and not having options for headphones and you know, whatever else. It's just like I've had that same desire and have built a device that accomplishes something similar myself as well. So it's I love that you saw that problem in your life and figured out. You know, you didn't have any prior experience, right? You said you're not an electrical engineer. You'd never done soldering before, but you didn't let that stop you. You're just like, all right, let's go figure out what needs to be done. And you went and you did the research and you figured it out and you made it happen. And I think that's absolutely brilliant.
Thank you. Thank you. I appreciate it. And yeah, it was one of those things I was hoping to broaden my experience, my skill base, and my knowledge by jumping into the project. As I mentioned, I'm pretty happy with version 2, but there's a couple of things I'd like to tweak, and I'm really glad to be able to talk with someone more experienced with audio engineering and more experienced with the audio wiring as well.
Yeah. So I'm going to change screens here to desk and face. Okay, so now you can see what is underneath. That is your slides. Okay. So you mentioned the Ham Nation presentation with Bob Heil talking about how to make a mixer. You sent me a link to that, and we'll make sure that these links to these products and pages get into the show notes. I did not copy them into the show notes for the live stream, but once this gets posted up for long term, I'll make sure they're in there. So here's the Building a Line Mixer, Ham Nation 164, on the Twit Network YouTube channel. Go check that out. And then here is a DIY 5-channel passive audio mixer by Masub. I don't know how they pronounce that channel name. But yeah, so lots of good materials out there for figuring out how to do this. And then these transformers. So I was looking at your schematic, and I mentioned before we started this that I think I might have understood what the problem was. Then I looked at your schematic. I'm like, nope, actually that wasn't the problem. You did it all correctly. And then there are the resistors. So they're 1K resistors. So let's take a look at, I want to go back to this page. And yeah, that's readable on the stream. So this, excuse me, this is your schematic. And you have a ground. Let's see if I can zoom in on this a bit. View. Zoom. There it is. 200. That didn't help much. Okay. But you have your ground and then left and right audio coming in from the back connectors. And you have ground and left audio going to the primary of the transformer, and then the lines represent the iron core, and then the secondary of the transformer has its own separate ground. So the fact that that ground and that ground, can you guys see my cursor? Yeah, you can. Okay. So the fact that that ground, the input ground and the output ground, are not connected to each other, that provides the ground isolation that you're talking about. Right? So the fact that these are not connected to each other is the important part. Now you do have that coming over here to the second transformer, but that's just because this is the transformer handles the left audio and this one handles the right audio. And so the primary ground comes over to this one and they're connected together, and that's fine because they share a ground. But again, that primary is not connected to the secondary. So you're still isolated ground here. And then again, you do have the secondaries connected because both left and right channels share a ground. But if you were to look at these, drawn side by side, you would see the input grounds coming in, and then there would be no traces crossing the transformer boundary. Everything would be coming in on the primary side would connect up to the connectors, and everything on the secondary side would connect down to your volume pots, and there would be nothing bridging across those two. That's kind of the important part from a ground isolation perspective. And you drew it up correctly here. And looking at how you wired it, it looks wired correctly because there's the ground wire coming into that side of the primary, and then that wire jumps over to that side of the primary, and then the secondary here jumps over to the secondary there. So just looking at the way it's wired, it looks like you wired it up correctly.
Yeah, I appreciate that. Just to make sure and really double check myself, as far as those transformers, I should see continuity between the left channel and ground on the input side of that transformer, and then continuity on left channel and ground on the output side, right?
Yes, because the transformer is just a bunch of wire, and as far as a continuity checker is concerned, that wire is just going to look like wire. It might have like an ohm or two of resistance, maybe a few tens of ohms, but it should really be close to zero between the left audio in and ground. But you should not have any continuity. You should not have any connection between either of the pins on the input side and any of the pins on the output side. Right? Between the input side and the output side, they should be totally isolated. There should not be any connectivity between those two.
Excellent.
Right?
Yep, that's what I'm seeing on mine, and I'm glad to get it reinforced that that is correct.
That is correct. Yes, it is. All right, and then on the output side of those transformers, again, your shared ground goes over and connects to the fully counterclockwise side of the potentiometer. And then the wiper, the center part of the potentiometer, is connected to your outputs, which are through these resistors. We'll talk about those resistors in a bit. So that the wiper is the output. And then the fully clockwise side of the potentiometer connects to the, which is the input to the potentiometer, is connected to the output of the isolation transformers. Right, so here's your isolation transformer, and it connects down to the fully clockwise all the way up on your volume pot.
Mm-hmm.
And then same with the left audio there. And these were 10K pots. He showed me, Ben showed me the link to the pot itself. Nope, not that one. Nope, not that. Maybe I closed it. Curses. I think I did. But the potentiometers you sent me links to, here, I'll open it up again. Potentiometers, 10K, volume control, potentiometers, yada, 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 except that it is a B-type taper. Where it is. There it is. So it's a B10K. I can't move my cursor over it because then it'll stop highlighting it. But the fact that it says B10K on the back tells me that it's not an audio taper. B is usually a linear taper. So an A would be an audio taper. Now, it's possible that different manufacturers call their tapers by different things. I know that different manufacturers will call it by different things, but I've never seen B represent audio. So the way you tell what the taper of the pot is when you turn it all the way to counterclockwise and measure between the wiper and the full counterclockwise, that'll be 0. And when you measure between the wiper and the full clockwise, right, so you've got the volume all the way down, it should be shorting your wiper to the ground side. Right? Because you want your output to be no volume at all, 0 ground. Whereas if you turn it all the way to the other side, so fully clockwise, then you want your wiper connected directly to the input. Right? So that whatever the input signal is that's coming in, the wiper will be connected directly to the input, and there's no attenuation whatsoever. And then everywhere in between, you've got some amount of resistance on top of the wiper and some amount of resistance to ground on the wiper. And what that ends up doing is causing a voltage divider, right? So you've got your input coming in. Here, I'll try and do it reverse because all this stuff does backwards. You've got your input coming in, and then you've got some amount of voltage or some amount of resistance, excuse me, then your output, then some more resistance, and then ground. Right? So that's a resistor, your output, and then ground, and another resistor, and then ground. And all you're doing is by moving that wiper, you're moving how much of that resistance is above it and how much of it is below it. And the total resistance of these two is always going to be the value of that pot, in this case 10K, right? So you will always have 10K total resistance. The only question is how much, where in that 10K is your wiper. And the difference between an audio taper and a linear taper is, what does that curve look like? So for, however much, let's say you're at 50%, you're straight up and down. A linear taper pot will have exactly half of the resistance above it and half of the resistance below it. So you should measure 5K between the wiper and the top side and the wiper and the bottom side. That would be a linear pot. But an audio taper pot is different. An audio taper pot is more logarithmic. And doing an actual logarithmic taper is actually quite difficult. So what they do is they kind of wave their hands at it and they say the lower part of the taper is going to go between 0 and 10% of the full value. And then the upper part of the taper is going to go between 10% and 100%. So it's kind of split into two different regions. So if you take that knob and put it right smack dab in the middle, halfway between fully clockwise and fully counterclockwise, and then measure between the wiper and the top and the wiper and the bottom, you should get roughly, if it's a 10K pot, you should get roughly 1K on the bottom and 9K on the top. Hand wavy numbers. The numbers are not exact. Instead of 5K and 5K, you should get 1K and 9K. And that's how you know whether it's an audio taper pot, is by measuring what the value is when the knob is halfway between the two. And what that ends up doing is it ends up giving you more precision on the lower volumes. Like if you use a linear taper pot in an audio situation, you'll have the volume knob all the way down in the all the way off section, and you just turn it up a little bit and you'll get a huge increase in volume. And then as you go past that, you get very little change in volume. Because the way your ear hears increases in volume is logarithmic. And so a little bit of a change at a weak signal sounds the same as a lot of change at a stronger signal. And so you want the actual change in signal to be proportional to how loud the signal is. So if it's a weak signal, you only want a little bit of change. If it's a strong signal, you need a lot of change. And so you want to have more control at the low end of your volume knob. And that's why it does like 0 to 10% over half of the swipe, and then from 10% to 90% over the second half of the swipe. Anyway, audio tapers versus logarithmic tapers. And Ben just sent me, continue the site. What is a potentiometer? If you
scroll down on that a little bit, there is a visual for what you're talking about.
Yep.
But I really appreciate you talking about the behavior, because that's something I haven't been able to find.
Oh, like why? What does it sound like if you get it wrong? That kind of thing.
Well, why do you want the logarithmic taper, and why do you want to, the sound to have more fine control there at the beginning or at the low range?
Yeah, and that has to do with human hearing. Yeah, okay. Yeah. So this, you can see how like the dotted line here is a proper logarithmic curve. And it's very difficult to actually do a proper logarithmic, but you can see how it does kind of a linear taper up to about 10% of the resistance over 50% of the position turn. And then it goes from 10% up to 90%, or up to 100% over the remaining 50% of the turn, right? So you kind of got these two separate linear sections. Nerd Garage says, I love how Mark explains things. Thank you. I appreciate that. So linear is B, is a common. Log or audio is A, is a common. You'll notice that there is no place that calls B an analog taper or an audio taper. So I really think what you have is a linear taper. Do you have precision control problems down at the low volumes?
I might, but I probably am taking care of that by adjusting the device audio.
Yeah, so you're pre-padding the audio before it comes into the mixer to
possibly
about where you want it to be. Yeah.
Mm-hmm. And then I have two additional levels two additional areas where I can boost the audio afterwards, either with the Bluetooth transmitter or my desk speakers.
You have so many places to adjust the volume that it's hard to tell what's where exactly. Yeah. Go ahead.
If I could jump in real quick, I wanted to say hi to Terry K4HNT. I see him in the chat. He's a member of my local amateur radio club.
Hey, Terry. And Troy Davis is also here, calls you, Ben, a brother from another mother, because he is Troy Davis.
Hey, Troy.
The Davis Club. And we got Steve. We already mentioned Steve. And I also see Tom, W8TAM, learning audio things today. Thanks, Mark. Well, thank you, Tom. Cool. So for volume knobs, there are definitely... No, we're not going to do that. There are definitely audio taper analog potentiometers, but I happen to be particularly partial to these stepped attenuators. Now,
okay.
No, not that one. There are a lot of different companies that sell these. I get them on eBay. They're about 12 quid a piece, so they're not cheap. But this is actually incredibly inexpensive for a stepped attenuator. You can spend several $100s on a single volume knob. I do not recommend this unless you are an audiophile that is used to expending buckets of money on things. But 12 quid a piece, I do recommend. These, if you can justify it as part of your project costs. Let's see if I can find one of these that shows the inside of it. You can see that from the outside they look like a normal potentiometer. Find one. There we go. But on the inside, rather than having a smear of resistive goo that you're swiping the contacts across, what they do is they have a series of surface mount resistors, and they are very precise surface mount resistors. And what it does is it ends up making a ladder that they can actually make it a logarithmic taper. So they can set the values there between each of the contacts to be exactly what they want. Now, this means that you don't have an infinite range, right? You have these individual steps between each of these resistors. And so that's why it says it's a 21-step volume control, because there are, I guess that makes it 20 resistors here that you can go like on the outside, and then 19 steps in between them all. But it is incredibly clean. Like, there are gold contacts here, not the resistive carbony contacts of a potentiometer, so you don't get that normal scratchy noise that you get from most, or that you can get from an analog potentiometer. and you know that your steps between are going to be very close to actually logarithmic. The other thing that is more important in an audiophile environment is that because these are very precise resistors, they're usually 0.1%, the matching between the left and right channels is incredibly tight. That is something that is also hard to do with an analog potentiometer, because the analog potentiometers are literally a goo that they just kind of wipe across the surface there, and if the goo is a little bit thicker here and a little bit thinner there, then the lines may not be perfectly linear. The line of resistance to knob turn may not be perfectly linear. It's probably not going to matter all that much in your use case, where it's mostly radios, but if you're doing audiophile stuff, stepped attenuators can be really nice. You can get analog potentiometers for a heck of a lot less than this. So if you don't need the features of a stepped attenuator, then by all means go for it. Oh, we've also got Smoking Ape and Kyle AA0Z in the chat room. Hello. Thank you, gents, for joining us. Okay. So, let's go back to this. And then the output from your pots, they go through 1K series resistors, and then each channel has its own 1K series resistor, and then it goes into a common bus, right? So the right channel here is taking the output from those resistors and tying them all together. And then the output of that just goes straight into your output connector. So the problem that you described was that even when your 6400 was turned off, actually I bet you didn't hear it when it was turned on, but when your 6400 is turned off, you could hear audio from a different channel coming out the speaker of your 6400. Is that right?
That's correct.
Okay.
That's correct. And you're probably right. I didn't hear it when it was on, and that might be because something else was filtering it out in the radio.
Wasn't filtering it out. It was driving it with a much lower impedance. So, all right. So this is what's happening here. You've got a signal coming in from one of your devices. Let's say this is your 7100. All right. And it comes in through the transformer. It gets isolated. And then it comes out from the transformer, it goes into your potentiometer. There's some amount of resistance between the input to the pot and the wiper of the pot. More importantly, there's also some resistance between the wiper and ground. So it's somewhere in the middle. It's not turned all the way down. It's somewhere in the middle where you can listen to it. So there's some resistance there. This goes into the series 1K resistor here, and it goes into the common bus out to your output. The problem is, it also goes through this common bus, through this 1K resistor, back into the wiper of this potentiometer, and through some amount of resistance here, out through the input into the isolation transformer, back out the other side of the isolation transformer, and into the output of your flex. Right? We're going in through the outdoor. We're one of my least favorite Led Zeppelin albums. So you've got power because none of this is 0 ohms to ground, right? And none of this is... It's a pretty high impedance signal because it has to go through all of these resistances. But you do have a signal through some impedance into the input of your flex. And if the active audio amplifier in your flex is turned off, right? So it's turned off. It's not driving the output to anything. So it's going to be a relatively high impedance because an unpowered transistor looks like a high impedance. So now that connector is connected to the speaker in your flex. Mm-hmm. And so even though it has to go through a whole bunch of resistance, it will eventually hit that speaker, go through the impedance of the speaker, and find a ground path. So that back signal has come all the way in through one radio, through your mixer, and back out into the speaker on your flex. And this is happening on all of your inputs. All your inputs are driving all of the other inputs. Don't want that. Now, the good news is it's relatively high impedance. In the absolute worst case, if you turn the volumes on all of these all the way up, so the wiper is connected directly to the inputs, and that minimizes the amount of impedance between the input here and the input here, right? That is the minimum amount of impedance. You still have 1K here that it always has to go through, and another K here that it always has to go through. So your minimum impedance between the output of one radio and the output of the other radio is always going to be at least 2K. And if you drive the speaker output from one radio through a 2K resistor to the speaker output of the other radio, those speaker outputs are usually in the order of like 4 or 8K. Or excuse me, 4 or 8 ohms, which is a much lower impedance, and that will absolutely dominate the circuit. So the speaker drivers, when they are powered on, they'll get a little bit of this signal coming in with a 2,000 ohm impedance on the input signal, and that'll just be okay. You've got a little bit of noise coming in. It doesn't matter. It's not. You're not going to damage anything, is what I'm saying. You're not going to damage anything by doing that. That's why these resistors are here. Okay, so think about that for a second. If you didn't have these resistors here, and you just tied the the wiper of these potentiometers together and connected them to an output. Like if you only had one of these channels and you didn't have all of the other ones, you wouldn't need this series resistor. You could just go straight from the wiper directly to the output channel, to the output connectors. And that would be safe to do. But because you have multiples of these coming together, you need to have these series resistors. Without those series resistors, if you ever turned this volume all the way up and this volume all the way up, you would directly connect with a wire, no impedance at all, no, just a wire, the output of this radio to the output of this radio. And that would be bad, because now you've got two output amplifiers that are trying to drive each other. Like, let's say one's got no audio at all and the other one's trying to go up and down. It's expecting an 8 ohm speaker to drive, but instead it has a 0 ohm amplifier that it's trying to drive. That causes all kinds of problems. Does that make sense?
Yeah, I think I'm following you. So I know you're going to pose a better solution for this, but before we go into that, can I ask you, is there anything I could add into my existing circuit that would, prevent that backfeeding of audio?
So, yes, but unfortunately it's going to require power.
Okay.
All right. You cannot do it.
I was just
going to
ask because I know voltage only flows one way through a diode, so I was wondering if there was, possibility I could throw a diode in there and have it where the voltage only comes in and doesn't go back out through the inputs.
So the problem is all of this is alternating current. It's all audio is AC. So what you would end up with is the positive half of your audio waveform. Let's say it's just a sine wave, right? You've got this nice sine wave. You're basically stopping the bottom half of that and allowing the top half of that to go through. That's called rectifier. That's one of the ways that you build a power supply. So a diode is not going to work in this particular use case.
Okay. Thank you for answering that.
Yep. So what you just described is a distortion pedal. If you're a guitar player at all, that's exactly how distortion pedals work. The distortion is clipping of your audio signal. You want to, stop it from going above a certain level, or in this particular case, stop it from going below a certain level. And they use diodes. They put diodes in circuits to do distortion. They do it intentionally in a distortion signal, in a distortion pedal, but in this case, it would be an unintentional thing. So, I'm going to bring up a KiCad. we're going to do a new KiCad, new project. We'll just do Ben's mixer. Okay. Oops. I didn't need to actually make a new director, but that's okay. And I'm just going to use this as a schematic drawing program. Okay, so let's drop a connector. TRS. Audio jack 3. So here's your input connector. Let's drop an audio transformer. And we'll go ahead and do the full thing. So we'll drop 2 of these. And we're going to draw it the way you have it. Oh, shoot. Okay. Our small. We're going to do it. Draw it the way you have it wired up right now. Oops, not yet. I've got to put the potentiometers here first. And that goes like that. And we'll do the other one down here. Shrink. Value 10K. Value, nope, they are the same part. Value 1K. Okay, so we'll do that. Oh, nope. And that, and okay. And let's drop some wires. Dinner is ready. Got to go run. Look forward to catching the rest on replay. Thanks, Terry. Thanks for coming out. Shield is our ground, so I will connect this to both of our primary inputs, and we'll call this the right channel, and we'll call this the left channel. Okay.
I was on mute the first time I tried to say it, but just wanted to say thanks, Terry, for joining us, and look forward to chatting with you locally.
Thank you very much, Terry. And Nerd Garage points out that I am drawing behind my face again. Thank you, Terry. Or thank you, Nerd Garage. All right. So we'll do that. And we'll do that. And we'll do that. And we'll do that. And then we will also tie these together, although that's not strictly necessary, but we're going to... Actually, I guess it kind of is. We'll do that. And then we'll put another one of these out here. Okay, so I think that's, yeah, Kyle. I've done a lot of KiCad in my time, so I know my way around KiCad pretty well. Kyle says, I love how Smitty just draws on that palette with ease, almost like he does it all the time. Almost crazy like that, huh? Okay, so I think this is what you have, right? So your connectors, your shield is connected to one side of the input of the transformers. And then the tip, which is the left audio, goes to one transformer, and the ring, which is right audio, goes to the other transformer. So that's the input side of your transformers, right? Does that look right?
Yeah. I'm going to have to learn how to use the software so I don't have to spend as much time on graph papers.
KiCad is pretty rad. And then on the secondary side of the transformers, again, we've got one side that is considered common. I'm calling it pin 3 here. That's all tied together. And then the other side goes to the top of our potentiometers, our volume pot. Same on both of them. And then the wiper of the volume pot goes through a 1K resistor, and then from there into the output jack. And I'm probably not going to draw it just for simplicity's sake, but we've got multiple copies of all of... Actually, no, I lied. I am going to draw it because we're going to need that when we start talking about how to fix this. So actually, now that I'm thinking ahead, let me do this differently. Okay, so we have multiple channels. Am I drawing under my head yet? No, I'm not. Okay, so we have multiple inputs here, each with a left and a right channel. So what I'm going to do is I'm going to connect all of these together, all the lefts together after their 1K pots, all of the rights together after their 1K pots, and then the output connector. Oh, and I've got to connect the commons together as well. Okay, so shield goes to the common, that's our ground. Ring goes to this one. So, right, ring coming in here goes to this transformer, that pot, blah, 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 into ring. Okay. And then tip goes to that one. Okay. So, add 3 more of these channels, and that's your mixer. Does that sound right?
I agree.
Okay. So, the problem here is that signal, as I was describing earlier with my hands, let's actually show it on the screen. Signal coming in from the tip on this goes through this transformer, goes up here through whatever impedance is visible on this pot, through that 1K, down here, through that 1K, through that pot, back through this transformer into the output over there. What we need to do to prevent that from happening is we need to prevent this node right here, which is called the bus. We need to prevent the bus from varying voltage. Okay? So what we would very much like to do is to hold this bus node at a fixed voltage. But that's hard to do because I've got signals coming in and out of it and all that fun stuff. So I'm going to ask you to take me at my word on a thing, because I will explain how it does this thing, but not necessarily why it does this thing. So I'm going to draw a bit more to this circuit, and it's going to be magical. So I'm going to move that over there. I'm going to do this so that I'm not drawing under our faces. And I am going to drop down an op amp. TLO 72, because we do need 2 of them. Okay, so I'm going to drop an op amp there and an op amp there, and then power. And those are 1Ks, so we'll use that. These will all be unity gain. Okay, so yeah, that's the negative input. We'll do that there, and then the same thing here. And then that one goes to that bus. Okay. And now this is ring. This is tip. And then sleeve still connects back to, you know what? I'm going to make this easier. Domini, Domini, Domini. I dub thee ground.
Well, after watching you do this, I'm going to have to go back and watch some videos about KiCad, because I know there's a lot of different keyboard shortcuts you're probably using right now in addition to mouse clicks, and you're making this look easy.
Yeah, it's like we said in chat room, it's almost like I do this for a living. This is literally my day job.
I'll say hi to Richard, G7EIX. Richard's another local ham. Glad to have him in here.
Perfect. Sorry I'm late to the show, Ben. I'll watch the whole stream later. With the G call, are you portable US or are you up really late? You said he's local?
He is local. Normally he operates as W4 G7 EIX or W4/, but he's right down the road from me.
Gotcha. All right, perfect. All right, so the last thing that, didn't want to do that. Last thing I did is just rather than tying all of the commons together, I just tagged them with grounds. So it's our ground. Now, with all of those grounds, is it any wonder we dedicate entire planes? Right, exactly. Jeff asks, with all those grounds, is it any wonder we dedicate entire planes of the board to it? That's exactly right. And for shielding as well. But all these connectors, all these components, except for these resistors here, have connections to ground. Okay. So what in the heck did I just do? Bring these in a little bit closer, and actually I'm going to zoom in a bit more so that we can see it because it didn't look like it was streaming well. So we still have, the signal coming in through the pot, going in through a series 1K resistor, through the bus, through the other 1K resistor, through this pot, and back out to the other audio. So all I did was disconnect this connector from this node, and I inserted these op amps in this way, or in this, I keep doing it under our faces, and inserted these op amps in between this bus here and the connector. And what the heck does that do? Well, let me show you one thing. Wikipedia.org. Op amp. Operational amplifier. Open loop, closed loop. Inverting. Seriously? Okay. There we are. Okay, so the inverting amplifier. This is a mode that you can use op amps in. There are several different ways you can wire up an amplifier, an op amplifier. And without going into the details of how an op amp works, I will summarize and say that the op amp's job is to change the output to make the two input terminals match. Right? So if the I guess I am going to describe what an op amp does. If the positive input of an op amp is more positive than the negative input, so if there's a higher voltage on this node than there is on this node, then the op amp will increase the output voltage of the output until they match. If the positive input is more negative than the negative node of the input, then it will decrease the output voltage of the output of the amplifier. That is all an op amp does. With that, you can do all kinds of math and all kinds of analysis and get the op amp to do all kinds of magic for you. We're not going to go into the details of that particular magic. I am, however, going to explain one mode of the op amp, and that is as the inverting amplifier. So how the inverting amplifier works is that if you've got a positive voltage on the V-in here, the op amp is going to do everything it can to keep that negative input at ground. So if there's a positive voltage here, this is ground. Positive voltage through a resistor to ground is going to create some amount of current there. The input to the op amp is an infinite impedance, hand wave. It's close enough to infinite impedance. There's no current that goes into the input of the op amp. So there's no place for that current to go except through this resistor. So there's a voltage here, a positive voltage, into ground. That creates a current through that resistor. That current has to flow through this resistor to the output. And the only way for that current to flow through to that resistor to the output is for this to have a negative voltage on it. And that's why it's called an inverting operational amplifier, because if you've got a positive input here, you'll have a negative output here. Similarly, if you've got a negative voltage here, you'll have a positive voltage here. So as the input goes up, the output goes down. As the input goes down, the output goes up, right? So they're constantly doing this. That's a simple inverting amplifier. And then how strong the output signal is compared to the input signal is determined by the size of these resistors, the input resistor and the feedback resistor. If they are the same value, then whatever voltage created that amount of current going through the input will be the same amount of voltage to create the same amount of current through the same resistor on the feedback. So it's 1 volt, 1 k ohm resistor, that's going to create 1 milliamp. To get 1 milliamp going through this resistor, I need to have minus 1 volt here and a 1 k ohm resistor here, and that'll create a 1 milliamp. So it's the same voltage. So if the resistors are the same, then the output voltage will be the same, but an inverse copy of it. We're not going to talk about gain here because I'm not actually trying to do gain. The important part about the inverting amplifier is that this node is always at ground. Always. At no point will this node right here increase in voltage or decrease in voltage, because if it did, then that would cause the op amp to change the output voltage here so that whatever current was flowing through here would bring this back into ground. Hand wave, I'm going to ask you to take my word for it that the op amp will make sure that this node is always the same voltage as this node. And since this node is tied to ground, that means that the input, the negative node here, is always going to be ground. All right? So what does that mean in our circuit? Well, what do we have here? I've got a 1 k ohm resistor going into the negative input and a 1 k ohm feedback tying the negative input to the output. That looks the same as this. 1 k ohm input into the negative terminal and a 1 k ohm feedback to the output. Right? So this is an inverting amplifier. But so is this. This is also an inverting amplifier. And since this node here is always going to be the same voltage as this node, which is ground, there isn't a way for a signal coming in here to impact this, because the way that happened before, let's say you pretend this op amp isn't here and you've got nothing over here trying to control this. This node will just vary up and down as the signals change. But whatever current comes in through this resistor, this op amp will draw that same amount of current out through the output so that it doesn't have a place to go through here. And so what you end up with is what's called a summing amplifier. We are going to sum, as an add, all the currents coming from this input through this resistor to ground, which is what this terminal is, and whatever current comes in through this input, through this resistor, to ground. And all of those currents are going to get summed together and forced through this one resistor and create a voltage on the other side. So this op amp in this configuration will consume all of these currents and do whatever voltage is necessary on the output of this to prevent those currents from flowing anywhere else. You know, this node is as if it were ground. You can literally view it as if I were to take this and tie it to here. And if that were the case, then it's kind of more obvious to see how a signal going through a 1K to ground and another signal going through a 1K to ground, those are not going to feed back to each other. Right? If you view it like that, those are not going to feed back to each other. But instead of this being a literal ground, it is the logical ground that is being created by this op amp because it's trying to keep this node at the same voltage as that node. Does that make sense at all?
It makes a lot of sense because you drew the pictures.
It's like, what you said made sense. I'm not sure I have internalized it.
No, really my question is, can we take it a step further then? And since you know the components I already have chosen for this project, what would you recommend for that op amp?
So neither of these are going to headphones directly. Is that right? You're not trying to drive a speaker with these. These are just line level outputs. One's going to a Bluetooth transmitter and the other one's going to a powered amplifier, right?
Yes.
Okay. So those loads will be at lowest 600 ohms, probably closer to 1K or 10K. The point of that being that you can use just about any audio amplifier, just about any op amp here, because pretty much all op amps would be able to drive those loads. Like in the absolute worst case, if they're both 600 ohms and you put them in parallel, that's going to be a 300 ohm load. Those op amps will be able to drive a 300 ohm load. Those op amps, most op amps may or may not be able to drive a 16 ohm load of headphones. Right, 16 is a lot lower impedance. It's going to require much more current, and it will cause a lot of op amps to distort. But line inputs are fine. And so you can use just about any op amp there that you want. I would recommend... So the difficult part here is not the op amp. The difficult part here is going to be the power supply. Okay. So, are you willing to say this has to be connected to an AC wall outlet? Or do you want to be able to power this off of a DC power supply, like a battery?
That's a good question, because if we went DC, couldn't I drive it off of a USB adapter or something? I'm assuming it's going to be a pretty low voltage.
Yeah, USB has other problems. USB power is incredibly noisy. Well, if you're driving it off of a computer, it's going to be incredibly noisy, and that'll come through in your headphone amplifier or in your op amps. The other thought I had would be like the 12-volt input, Anderson power poles, or the 12-volt system from your radios.
That's actually what I was going to say. If we wanted to, say for the purposes of the conversation, I know that I can add a couple extra outputs to my shack power supply. So I could probably drive or probably come up with another 12 volts.
Okay. Nerd Garage says that my audio just went derp. I don't know can you expand on derp, or how long did it go derp? Sorry about that. And Ben, I assume you didn't hear anything?
I did not hear any issues.
You didn't hear any derp? Okay. Interesting. Not sure what that was. Your audio is fine now. Sounded fine to me the whole time. Okay. Wow. Interesting. Okay. All right. So I was dealing with that. Say again what you just said.
I've got a spot where I could get 12 volt or, 13.8 volts off of my shack power supply. I could do that.
Okay. So if you can get 12 volts, O1, XO2, we're going to create a 2-pin connector here of a power input. All right. We're going to design you a small power supply. Polarize small. Actually, all right, let's do it right, and then you can ignore some of these if you want. Polyfuse small. Value. That'll be plenty. DIODE. Nope. D small. There we go. Okay. So we're going to do this with 12 volts instead of AC power. That's going to have a couple of ramifications that we will have to deal with. 1N4001. Good enough. I was going to say, even the 12 volt off the bench power supply is pretty noisy these days, but I see we are putting filtering in. I'm going to be putting in a regulator, which will get rid of a lot of it too. So, okay. Farads. And then C small. And we'll call that 1 microfarad. Ooh. Are you going to be modifying your existing board, or are you going to build a revision 3?
Probably a revision 3, since it sounds like we're going to be adding to the circuit.
Yeah, we are. Okay. Then in that case, we'll do that. And I will go ahead and do another one. Value 0.1 UF. Okay, cool. Actually, hey, knock it off. 1 nanofarad. We'll do 1 nanofarad. Okay. So now we're going to do a 7809. Let's give ourselves plenty of overhead. 7809. So that is a voltage regulator. And then we're going to need... Actually, we don't need that one here. We're just going to do those. And we're going to copy those to the output. Okie dokie. So, lots of grounds. I'll explain what all of this is in a second. Yeah. Okay. And we'll do plus 9 volts. And Domini, you are 9 volts. Okay. While we're here, let's go ahead and hook up power to our op amp. And let's decouple that op amp.
Smitty, would you slide us over a little bit to the right?
Womp womp. Thank you.
Thank you.
Okay, so let's talk about what in the heck did I just do. So here's our input. I just use a generic 2-pin connector. You can use like barrel plugs or Anderson power poles or whatever you want. And then I put a fuse in line. Again, you don't have to do the fuse if you decide not to, but I put fuses in my design. And then I have a reverse voltage protection diode. So what happens here is if you this is the positive input and that's ground. If you accidentally flip those two, then you're going to end up with a negative voltage on here relative to ground, right? Because this will be ground and this will be positive 12 volts. That's the same thing as putting negative 12 volts here in ground. What that'll do is that'll draw a whole bunch of current through ground, ground over here, that way through your diode, and that whole bunch of current will flow through the fuse, through the input connector, and will pop that fuse.
Okay.
So if you hook up your voltage backwards here, that fuse will pop because a whole bunch of current is, you've basically just shorted your minus 12 volts to ground directly. And so that's going to pass a whole bunch of current through there and pop that fuse. But if you have a positive voltage here, it'll hit that diode and the diode's going to go, no current flow. And so a positive voltage will exist here quite nicely. And then we've got the 100 microfarad and a 1 nanofarad capacitor here. What the heck are those for? They are arbitrarily chosen values. Basically, a bulk capacitor, that's going to say we're going to store up a whole lot of energy in here so that if there's any big changes in current draw or big changes in voltage coming in or whatever, those changes will get smoothed out by this 100 microfarad capacitor. So it's filtering out large changes in either current draw this way or voltage supply this way.
So by adding those two components, if I'm using my Shack's power supply and I say key up on the HF radio at 100 watts, that should prevent me from having any kind of negative impact on my audio.
That's a theory. You bring up a good point. Let's throw an inductor in here. We're going to put a series inductor in here as well. I think that's a good spot for it. Nope. Kind of feel like I want a capacitor before it as well, but okay, we'll do this. And then the exact value of this is somewhat arbitrary. 10 microhenries. We'll go with that. So that's just an RF joke. So power rail doesn't get modulated as an input. Well, yeah, yes. So any noise that comes in on this line, some of it will get blocked out by the voltage regulator, but the voltage regulator has what's called a power supply rejection, and it's not perfect. So whatever the voltage regulator, whatever noise comes in here, some of it will pass through the regulator and get sent out to the output. If you have noise on your 9-volt line, that'll show up in your op amp, is really what it boils down to. And so we want to eliminate as much of that noise as we can. We're going to do part of that by putting a series inductor, which will look like a high impedance to RF. So it makes it very difficult for RF to get through this path, but it's a low impedance to DC, so DC will pass through that no problem. And then these capacitors will look like a low impedance to RF. And so any RF will get shunted to ground. And all that current will just go straight to ground before it ever hits the regulator and the rest of the system. And they do that by storing a charge. The 100 microfarad is there for large swings, typically low frequency swings, and the 1 nanofarad is there for higher frequency swings. So like a very large capacitor doesn't react very quickly. So it'll work great for large low frequency things, but it doesn't work very well for high frequency things. And so the 1 nanofarad is there to capture the high frequency things. Nerd Garage is saying I could be wrong, but I thought he was asking about the cap preventing any voltage drop on the bench power supply when keying up from affecting the power supply. Is that what you were talking about? So if you key up on 100 watts, that the voltage input on your bench supply will drop?
Yes.
I misunderstood your question. So no, it will not work with that, because 100 microfarads is not big enough to do that. If this input here were to drop below what the voltage regulator wanted for an input, that 100 microfarad capacitor would empty in less than a second. So it will not be able to drop. It will not be able to handle a long-term voltage drop. But the good news is that our power input here is going to be 13.8 volts, 12 volts, 14.6, whatever. That's why I selected a 9-volt regulator here. So 7800 series are voltage regulators. 7805 is a 5-volt regulator. 7809 is a 9-volt voltage regulator. 7812 is a 12-volt voltage regulator, and so on and so forth. So this is a 9-volt regulator, and they typically have 1 or 2 volts of dropout, meaning that your input needs to be 1 or 2 volts higher than the output voltage for this thing to regulate correctly. So to have 9 volts output here, we need to have at least 10 or 11 volts input here. And so if your power supply drops below 10 or 11 volts, then your output here will start dropping as well. But as long as your input, your power supply is at least 11 volts, then this will output a stable 9 volts. Does that make sense?
Yeah. So as long as whatever power is coming in is above that 9, or above a threshold that's above 9 volts, it should not be an issue.
Correct. So the voltage regulators need about a volt or two. Crummy voltage regulators, cheap voltage regulators, need about a volt or two to do their job. And if they want to output 9 volts, they need another volt or two on top of that to make that 9 volts clean on their input. So for 9 volts output here, you need at least 11 volts input here. Now, there are voltage regulators that are called low dropout. So if you've ever heard the term LDO, if anyone refers to a voltage regulator as LDO, what that is, it's generally used very generally to refer to any voltage regulator, but really it's a specific type of voltage regulator. 7800 series are not LDO, so they're going to require things. You can put the pinouts on these are exactly the same, so you can put just about any voltage regulator here. I just chose a 7809 because, again, the pinouts are the same. Anyway, so we got our decoupling capacitance on the inputs and outputs of our voltage regulator. Now we're going to have a nice clean 9 volts output here. All of these caps need to be very physically close, laid out close to this voltage regulator. All right, so that's going to try and block some of the RF. That's going to shunt some of the RF to ground. Our regulator is going to give us a nice solid 9 volts out. Some more decoupling over here. We're good to go. So, here's a problem. All of our audio here is ground referenced. So this signal is going to go up above ground in a positive voltage and down below ground in a negative voltage. And so half of the signal is going to be above ground and half of it's going to be below ground. But we've only given our op amp a positive power supply. This is why I was asking you whether you were willing to commit this to needing AC power. Because if you were willing to give it AC power, then I would design this power supply in a different way that would give us both positive 9 volts and negative 9 volts. And then this circuit as drawn would work.
Okay.
So that's one way to do it, is to use an AC input, and then you end up using an isolation transformer, and you ground the center and blah, 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 with the diode bridge and various other things. You end up with a positive and a negative voltage regulator. And it gives you positive and negative voltages above and below ground. We don't want to do that. So instead, what we have to do is we have to generate our own ground. It's a virtual ground. It is a voltage that is halfway between our positive supply, which is 9 volts, and our negative supply, which is ground. So we need to generate a power supply that is at 4.5 volts. One way we could do this is by copying this and sticking, instead of putting a 7809 here, we could do, they don't make 78045s, but they do make 7805s, which are pretty close. So we could drop a 7805 here and then call this 5 volts plus 5. We could do that if we wanted to. So we have one input filtering and then 2 output regulators, one that creates a 9 volts, one that creates a 5 volts, and then ground. And those are our power supplies. There are various different reasons that that's not the preferred way to do it, because now your middle voltage is not perfectly centered between 5 volts and ground. And especially if you start dropping input voltage here, your 9 volts will start getting, that'll become 8 volts, which gets even closer to here. And so your middle voltage is not actually the middle. What would be better, oops, I don't want to actually grab that indicator or that thing, yeah. What would be better is to make our own power supply using a voltage divider. So I'm going to change that value to 10K. I'm going to copy it. I'm going to make another one here. I'm going to grab that, put that there, put that there. Okay. So if I have 9 volts here and ground here, and I've got 2 resistors that are of equal value, that's going to pass some current through here, and it's going to be the same amount of current going through there than it is there, because there's no other place for that current to go. And Ohm's law says that the voltage draw across that resistor and that resistor have to be the same, because they're the same value and they have the same amount of current. Which means it's going to be 9 volts and ground. Each of these is going to take half of that voltage. This node right here is going to be 4.5 volts. It is going to be exactly half of this voltage here. If this voltage changes to 8 volts, this one will change to 4 volts. If this changes to 10 volts, this one will change to 5 volts. This is always half of our VCC. Okay? So that will always be perfectly centered between your input power and ground. The problem is that as drawn, that's a 10K impedance. If I come along and try to use that as my ground here. So what we're doing is we're going to be replacing all of these ground signals with this new virtual ground that we're generating. So if I were to come along and say ground A, we're going to call this our analog ground. It is not a power ground. We are generating our analog ground. And now I want to start using that analog ground everywhere. Oops. Everywhere that we are running an analog signal into ground. Yeah.
So I see you copying and pasting instead of renaming those nodes. Is that because this is actually going to drive downstream in the program?
So yes. So KiCad, that is an artifact of KiCad. The library component that I'm using is called ground A. If I were to just rename them all that would do would change the value, which is an arbitrary string. It doesn't actually change what the component is. And so it would look like ground, or it would look like ground A, but it would actually be tied to the ground node. So with power nodes, it's really best to come over here and select the actual power node that you want. So there are lots of different power nodes that you can use. Like we chose plus 9 volts. There's also a plus 9 VA and stuff like that. But these are all different. They're all different. But unfortunately, you can change what they look like without actually changing the node that they're connected to. Like, I think I can change that from ground. Will it let me? Value. Oh, no, it won't actually let me. That's new. It used to let you change it. I'm glad it doesn't anymore because you really should not be changing the names. So now it won't even let me change the name of that.
Okay.
So that's good.
I appreciate you diving into that. I didn't want to pull you on too much of a tangent, but as a software nerd,
yep,
yeah, I appreciate it.
Absolutely. Okay, so those are all of our ground A's. Now the problem with this is that ground A here is like a 10K ohm impedance. It's actually 5K because it's both of those in parallel. And if I stick a 10K ohm resistor between here and here, that's going to change our circuit. It's also going to be a 10K. It's also going to be a 10K resistor between here and here, right? So that is not what we want. We want to have something that is a very low impedance because the rest of the places that this circuit, this voltage is used are relatively low impedances. So we need something that's going to make this VCC over 2 signal a much lower impedance. And a common way of doing this is with an op amp. So we are going to use another op amp, and we're going to configure it as a voltage follower. And then we're going to take that and go like that. Okay, so what is a voltage follower? A voltage follower is, remember how I said that the op amp will do whatever it needs to do to make sure that the inputs are the same. So if you put a voltage on the positive input, okay, and let's say that you've just powered this thing on and it's got 4.5 volts coming in the positive input, but it hasn't done anything, so the output is 0 ohms. Well, that 0 ohms comes right back around into the negative input. The negative input is more negative than the positive input, so it will start increasing the output of this voltage because those inputs do not match. I've got 4.5 volts on the positive input and 0 volts on the negative input. The positive input is more positive than the negative input, so it will start to increase the output. It will increase that output continuously until the output hits 4.5 volts, at which point now 4.5 volts appears on the negative input and on the positive input. Those voltages match, everything's happy, and it stops moving. It stops changing its output. So basically, whatever voltage comes in on the positive input, because the output is tied directly to the negative input, it'll be that same voltage on the output. But because it's being driven by an op amp has an incredibly low output impedance. So it can drive a lot more current than these 10K resistors can.
Okay.
So the voltage divider here generates the voltage, but it's a high impedance. And so we feed that high impedance into the op amp in a voltage follower mode, and that lowers the impedance. It's the same voltage on the output, but it's a much lower impedance. And that lower impedance will now drive all of these places that we are using that voltage. Analog ground, all over the place. Okay? Except we have one more problem we need to solve. And that is that your output needs to be, your analog or your audio needs to be ground referenced. So here on the inputs, these inputs go up and down around ground. But we have a transformer that's performing that isolation for us. And so we are generating our own analog ground. And so the audio on this line will be going up and down above 4.5 volts. So if we've got a 1 volt peak-to-peak signal, it'll go up to 5 volts and down to 4 volts and up to 5 volts and down to 4 volts. So it will be oscillating around the center point, which is 4.5 volts. And that's okay because that's 4.5 volts, that's 4.5 volts. So all of our grounds are 4.5 volts. And we come over here, the op amp, we've given it 4.5 volts for our ground. So this voltage here will be the same as the voltages over here and everything. So now my signal here is cycling around 4.5 volts. Goes up to 5 volts, down to 4 volts, up to 5 volts, down to 4 volts, into your speaker or whatever your load is here, and then down to ground. We don't want that because that's a 4.5 volt DC voltage through that load, whatever that load is. In your case, it's going to be like the line level inputs on your Bluetooth transmitter and your powered amplifier. These need to be going around ground, not around 4.5 volts, because that 4.5 volt DC will cause us some problems. So the way we fix that is by using a couple of these. So one of the neat things about a capacitor is that it will pass an AC voltage, but it will block a DC voltage. There we go. Okay. That's a little ugly of a layout, but yeah, we'll fix that. Hold on.
Yep, that looks better now. It's clear that those are two separate capacitors.
Yeah. Am I? Okay. I'm not drawing underneath my head. Okay. So now what's going to happen here is that the analog audio is going to pass through this capacitor into this connector, but the DC will get stopped by that capacitor. And so now there will be a 4.5 volt charge on that capacitor where this side is oscillating around ground and this side is oscillating around 4.5 volts. So just by putting those capacitors in series, you are blocking the DC. So you'll often hear the term DC blocking capacitor. That's what this is. Okay. I think that's it. So this over here is what you already had. So we haven't changed any of this, except by renaming this common node that you had. What we have done is we have inserted the op amps here, one per channel. We're using them as summing amplifiers to sum the currents coming from all these different input channels. I've only drawn 2, but there are a total of 5 in your mixer. And you can just add more and more. You can keep adding as many input resistors into this node as you want. And just whatever currents are coming in, they will all get summed together and sent out through out the output of this op amp. And then through the DC blocking caps and then to your output connector. And then we built a power supply because, you know, these op amps need power. They cannot work without power. And so we get our 12 volts in here. We have a little bit of protection. We have a little bit of filtering. Then we have our 9 volt regulator and a bit more filtering and capacitance. And then now we've got a strong 9-volt signal. We've send that 9-volt signal into our op amp. That's just the power supply. Those are the power inputs for the op amp. U1 is the... am I drawing under my head? I am. U1A and U1B, there's a single chip that has 2 op amps inside of it. So it's one chip with 2 logical circuits inside of it. And then that single chip also has power pins. So pins 1, 2, and 3 are one op amp, 5, 6, and 7 are the other op amp, and then pins 4 and 8 are the power pins for that 8-pin chip. And then, for reasons I won't get into here, you need to add some decoupling capacitors right next to your op amp. So you need to have these capacitors on the power supply very close to the chip. I won't get into the gory details of why you need that. Okay, I guess we don't need this anymore. And then the only thing left is that we need to be able to generate this virtual ground here. And since we're just going to use the same op amp chip that we have here so that we don't have multiple things in our bill of materials, let's create... U3... This is the B node. There we go. Okay. Actually, oops, shit. So what I'm doing here is, because these op amps come to a package, and we have an extra one here that's sitting there doing nothing, we're just going to go ahead and put it in parallel with this one, and it's going to do is it's going to double the current handling capacity of your virtual ground circuit. It's going to make it so that it can handle twice as much power. It's going to make it twice as good, quote unquote.
But that's just kind of a freebie because we're looking at a op amp that would serve 2 circuits in the example here.
Correct. Yeah. If we were designing this and either with single unit op amps like a TL071, that 2 there means that there are 2 to the package. A TL071 has 1 in the package, and yes, there is a TL074 as well, where you can get 4 op amps in a single package. If we were using a TL071 here, then we wouldn't bother with this. But since we're using the dual packages for all of these because they're all stereo, just use the same chip. We get a free op amp, and we'll do that. The only thing is that you don't want to connect their outputs directly together. So we are going to stick 1 ohm resistors here so that there's just a little bit to prevent them from fighting too much. If there's a tiny difference in voltage between these outputs, that difference in voltage will get dropped across those resistors. You don't want them like fighting over like a 1/10 of a volt or something like that, right? Just let it dissipate that 1/10 of a volt. That's fine. And then your your analog ground will be the average of those 2 voltages. Oh, one more. We'll copy that. Okay. Go ahead. Did you have a question?
I was just going to say, it looks like I can get a TL075, which would be great since I was hoping for 5 inputs.
TL075? I'm familiar with 1s, 2s, and 4s. TL075.
No, I'll take it back. I think I'm messed up my search there. No?
Okay, keep in mind that the 072, first off, we're not going to be using TLs. That's a TLC 075. Quad 16 volt 10 megahertz operational amplifier with shutdown. Okay, so but it's not a 5 channel op amp.
Okay.
It's a different part. But remember that these are all stereo inputs. So you're going to need 2 Wait, no, you don't need one per channel. You only need one for the mixer. Doesn't matter. You can add as many input channels as you want here. You only need a single TLO72, or I keep saying TLO72 is a shorthand. We're actually going to get you a much better op amp than the TLO72. They're pretty crap. But it's kind of the quintessential op amp, but they are crap. Anyway, you only need 2 channels here. It doesn't scale with the number of inputs because the number of inputs just adds the number of resistors here. I got one resistor coming in and another resistor coming in and another one coming in over here, but it's only a single mixer amplifier that's needed for all of those inputs. Okay. Actually, hold on. Let's do this. Zoom to objects. I think that's everything. I think that's everything that you need.
Okay. Just to hit you with a couple of questions.
Yes.
Since you had 9 volts called out there, I don't want to draw you into completely redesigning the circuit, but I was just curious, in place of a 9-volt input, could I use a 9-volt battery?
You could, yes. So the concerns with the 9-volt battery is that they cannot provide a lot of current. Now, the good news is these op amps, if you're driving line level here, your current draw is going to be determined by how much power is being drawn out of those op amps. So if you were to drive headphones here, the headphones are pretty low impedance, and they would pull a fair amount of power that the 9-volt batteries may or may not keep up with. Line level outputs, those inputs to your Bluetooth and your Bluetooth transmitter and your powered speakers are probably going to be somewhere between 1K and 10K. Put 2 of those in parallel, even if it's 1K, that's a 500 ohms, sending a volt or 2 at most into that. You're looking at a few milliamps, and a 9-volt battery will be able to handle a few milliamps, no problem. So a 9-volt battery would work well here.
Okay. Just wanted to ask it because you're the man to ask.
Yep. Yeah. Any other questions?
Just for my curiosity, if I had said I'd be okay dedicating AC power to this instead of DC, how much of the circuit would change?
So what would change would be this power supply would change. We would be able to remove this entirely because the instead of having 9 volts ground and analog ground, we would have positive 9 volts ground and negative 9 volts out of our power supply. So we wouldn't need this to generate our third supply. Making sure I'm not drawing over my head or under my head. We would not need this to generate our third power supply. We would get it all out of this power supply up here. So this would go away entirely, and this would be replaced with a bridge rectifier, then 2 copies of all of that. Except with a different chip here, a 7909. So let's draw it. It won't take long. Add a hierarchical sheet. Dual supplies. Sure. Go there. Okay. So I have an empty sheet here. So let's draw what this would look like. O2. So there are 2 different ways of doing this. You know what? Fuck it. Let's do it right. Okay. We are going to use a 3-pin input. So what this is our 3-pin wall plug. Okay? So we got a live, a neutral, and a ground. So let's tie our ground to ground. That's our ground pin. Value AC input, 120 volt AC input. All right. Then the first thing we're going to do is we are going to go to a transformer. Not an audio transformer. With a center tap. Okay. That's our transformer. Okay. 120 volt in, 12 plus 12 volt out. Okay. So we are going to take our AC and we're going to connect it directly to the primary of our transformer. Okay. So we have 120 volts going across this power transformer. The output of this is, so this is what's called a center tapped secondary. So you can see that it's got the secondary coil here, but it has a tap in the middle of that coil. All right, so I can get to a voltage right, between 3 and 4 will be one voltage, between 4 and 5 will be another voltage, and then between 3 and 5 would be the sum of those two voltages. So you can either view this as a single 24 volt output if we use those two taps, or I can view it as a 12 volt output from here to here and another 12 volt output from here to here. All right, and that's what we're going to do. So then I'll show you how we end up using that. We're going to tie that one to ground. And now, since I've tied this to ground, when this side is positive, this side will be negative. And when this side is negative, this side will be positive. Because I am anchoring the middle of that transformer coil into one spot, into ground. And so now the two different halves of the transformer are going to be pushing in opposite directions. Bridge rectifier. Sure.
And just to make sure I'm keeping up, that's in AC, right?
Yes, all of this is alternating current.
Okay.
Now, we go into a nifty device called a bridge rectifier. A bridge rectifier is 4 diodes. And those 4 diodes are configured in a sort of magical way where all the negative voltage comes over here to this output terminal, and all the positive voltage comes over here to this output terminal. So coming in here, I've got full analog, like brief network congestion. Interesting. So Nerd Garage is pointing out that my audio just went derp again. So many core electronics and ham radio concepts wrapped up in one well-explained video. Thank you, Nerd Garage. Anyway, so I'm sorry. Into 3 and 4 on this bridge rectifier, they are full analog signals like this. On the negative side, anytime that sine wave goes below ground, right? So that bottom half of that signal is going to show up on this pin here. Similarly, the top half of that signal is going to show up over here. So through diode magic, this will be a positive voltage. Now, it'll be a positive voltage going up and down, but it never goes down below ground. So it's still got these giant humps in it, like the half of a sine wave, and it goes back down to 0. It doesn't go below 0, but then the other side is now generating the other half of the sine wave. It's what's called half wave rectification, is when you've got your sine wave, and you basically take the bottom half and you fold it up on top of, bring the bottom half, rotate it up into the top half, and so now it's got like these multiple hills, right? And then we're doing the same thing on the negative side where, I've got one AC signal up here and I've got one AC signal down here. On the other one, we're taking all of the negatives and folding them down. So out one side, I've got all the positive halves of these signals, and on the negative side, I've got all of the negative halves of these signals. But the signals are still very bumpy. So this is where those those big ass capacitors matter a lot more. So this is a very large capacitor, 100 microfarads. And this is going to matter a lot more here, because what that's doing is that is leveling out those big humps. Right? Now it's going to make it a relatively consistent. It's still going to have a little bit of wobble at the top, but you've gotten rid of all of that down into down all the way down to 0 voltage ranges. Those 100 microfarad capacitors are going to flatten out that AC signal. At least they're going to go a long way toward doing that. And then we still want the 1 nanofarads, because those are going to be getting rid of our any RF coming in. So the same reason we wanted them in the other one, and I'm starting to draw under our heads again. Oh, whoops, haha, I just realized I did something wrong. Because these are negative voltages, not positive voltages. Okay. So all of these are connected to ground. Okay, and now we're going to do the 7809. And we're going to do a 7909, which is a negative voltage regulator. It's the exact same thing as a 7809, except that it does negative voltage instead of positive voltage. So this top half is going to look a lot like the power supply that we did on the other page. And we're just doing the exact same thing, but mirror imaged on the bottom. And I'm just going to copy all these again. Oh. All right. So now, plus 9 volts up here, and minus 9 volts down here. So, well, even though that's redundant as far as the KiCad is concerned, I'm going to draw that just to make it more clear. So what have we built? Well, we've got our 120 volt AC plug. Sorry, Europeans, this is American voltage. We got 120 volts AC coming in. We have our ground tied to the service ground, and neutral and hot going into the primary of our transformer. Our secondary of that transformer are two 12 volts, or it's either a single 24 volt with a center tap or two 12 volts, depending on how you look at it. Electrically, it's all exactly the same. So now I've got this ground here, and when this is creating a positive 12 volts to that ground, this is going to be creating a negative 12 volts to that ground. And then it'll be alternating back and forth between those two states. We take that positive voltage coming in here, and it'll pass through that diode over here to this positive side, And this is a negative voltage over here. It'll take that negative voltage, go through that diode out to the negative side. And then these alternate, and now this is negative and this is positive. So this is going to come in, and this negative voltage will pass through that diode and create a negative here. And this positive will come in through here and go through that diode and create a positive here, right? So all the positive halves of these AC signals are coming out through this wire, and all the negative halves of these AC signals are coming out through this wire. Does that make sense?
Mm-hmm.
Okay. So now we have a positive half of an AC signal coming in here, which is very bumpy, and we feed it into these capacitors here, which filter out those bumps and leave it with a mostly flat. It's not perfectly flat. There's still a little bit of warble up there, but a mostly flat 12 volts. It's actually closer to 18 volts because that 12 volt is RMS, and this is going to be the peak voltage of that RMS, which ends up being about 18 volts, somewhere between 17 and 18 volts. This will end up being that peak. So you actually end up with like 17 volts here, with like 1 or 2 volts, about a volt plus or minus of warble at the top. That comes in, and you regulate that, and you get a nice clean solid 9 volts out here, and then more filtering there. Same thing down here. You got a negative 17 volts plus or minus a bit. Regulate that down to negative 9 volts, and you have your 9 volt supply here. So now I've got positive 9, negative 9, and ground. Let's go back over to our analog circuit. Instead of having positive 9 and ground feeding the op amp, I would do positive 9 and negative 9 on the op amp. So the op amp's power supplies would straddle ground. And actually, because we're doing positive and negative, I would probably go to 5 volt regulators here. So you had positive 5 and negative 5, and which would give you a total of 10 volts of headroom, 10 volts from top to bottom, right? Whereas you could use 9 volts as well, and then you would have 18 volts of headroom. You'd have plenty of headroom. You would not distort at all in any of these levels that you're likely to see here. You'd just be burning a lot of power in your op amps, but that's okay. So I would change that positive 9, or that positive 9 would stay there. I would change that to a negative 9. And then I would get rid of all of this because we don't need that to generate our fake ground. And I would change all of these analog ground references to our real ground. I would change them back to just GND. Okay? And then we could even get rid of these capacitors. Although, I just realized that was underneath the thing. We could get rid of these DC blocking capacitors because this will putting out a signal above and below ground, actual ground at that point. Having said that, it's generally a good idea to leave those capacitors there anyway because op amps will always put out just a little tiny bit of DC voltage. It's their common mode. And those capacitors there are a good way of basically covering up the little bit of DC voltage that op amp is always going to cause. That's especially important if you've got 2 op amps in series. Let's say for some reason you needed an op amp over here as well. And if that op amp output a little bit of DC voltage, and then you came over here and gave gain on this op amp, whatever, let's say it had 1 millivolt of DC voltage coming in here, and you had a 10-to-1 gain here, then this would be putting out 10 millivolts of DC voltage. So anyway, put your DC blocking capacitors in, except for very specific use cases where you need it to go all the way down to DC. This is not that use case. Throw the DC blocking capacitors in there, and it'll save you a lot of headache. Ask me how I know. Again, I think I was pointing at things underneath my head. So that's how it would change if you're willing to deal with an AC power supply.
Okay. Smitty, I think you've given me version 4 and version 5 now. And I really appreciate you running through this. After you and I talked on Discord, I tried to go out and learn a little bit about op amps. I didn't feel comfortable with them before. I feel comfortable with them now, and I really appreciate you breaking this down into terms that I'm able to wrap my head around.
I'm glad I was able to help out with that. Op amps are one of those things that, for such a simple device, they can be used in so many ways. And when you look at the simplicity of what they do, literally all it does is, if the positive input is more positive than the negative input, it will increase the output. If the positive input is more negative than the negative input, it will decrease the output. That's it. That's all it does. But with that simplicity, you can do so much with them, and they can be used. It's like chess, right? The rules are simple, but the way those simple rules get put together can result in incredibly complex things. Op amps are like that. The way you can use an op amp, you can use op amps to do some serious magic. And we're talking about a relatively simple one here, like the inverting input. This is one of the first things they teach you about op amps, the inverting amplifier and the non-inverting amplifier. Where's the non-inverting amplifier? See, like they even taught you the inverting amplifier before they taught you the non-inverting amplifier. This is the non-inverting amplifier. So if you want an amplifier that where the output and the input are the same voltage, this is the way you would wire it up, right? The problem with the non-inverting amplifier is that it does not give your input a fixed ground voltage to dump its current into, right? So as a mixer, it wouldn't prevent the crosstalk that you're seeing, right? We explicitly want the inverting amplifier because this node is always the fixed voltage. That fixed voltage is explicitly what we're looking for here. So here's where it's describing the summing amplifier. So this operational amplifier applications is the Wikipedia page that I'm looking at here. The summing amplifier is what we're doing. You have this, some voltage going through a resistor, into this bus, and that bus goes into the negative input of the amplifier and through a feedback resistor to the output. That is exactly what we've drawn here. We've got some input here on these volume knobs through a couple of resistors into a bus, into the negative input, and then a feedback resistor going to the output. That's all we've drawn here is this summing amplifier. And that summing amplifier is just a special case of the inverting amplifier where you've got more than one input resistor. If I tack another input resistor here, it looks exactly the same as the summing amplifier. Or maybe I should say that the non-inverting is a special case of the summing where you only have one input. Anyway, but yeah, you start getting down into like instrumentation amplifiers and wine bridges and integral. You can actually use an op amp to perform integrals, like analog computer, like calculus. An op amp can do calculus for you, right? Like the ways you can connect this thing up to get it to do weird stuff. They're just endless. And it's just this one device that does that one simple thing. It compares the two inputs, and if one is more positive than the other, it increases its output. If one is more negative than the other, it decreases its output. That's all it does. But you can use it to do so many things. So just start out with like the two simple cases of just an amplifier. You look at how these resistors compare to each other, and that can give you gain. We have it so that the resistors are the same, so that's called unity gain. There's, the gain is 1. So the output voltage will be exactly the same as the input voltage, the way we have it configured here. This is a voltage follower, which is another gain of 1 amplifier. Just start with those and kind of wrap your head around how those work and what they do and get comfortable with that. And then you can start using them in circuits, and then you can start finding other ways of tweaking things and whatnot. So, yeah.
This will be great, and I appreciate you explaining this on a live stream. That way I'll be able to go back and reference this later.
It's like, I don't have to take notes. It's all being recorded. Yeah, and we've got a bunch of folks in the chat room, so thank you everybody in the chat room for hanging out with us and for asking questions. Jeff also points out, it's like, I mean, given the components, it might work on 240 volts. He's talking about the AC power supply, the dual power supplies down here. I have it listed explicitly as 120 volt input. If you put a 240 volts there, it just means you'll get 24 plus 24 volts out here. Yeah, that'll probably work on 24 volts, no problem, as long as these capacitors are rated for the 24 volt input. Actually, it'll be closer to like 34 volts, 35 volts because of the peak voltage. So as long as these are like 50 volt capacitors, you'll be fine. And then as long as you're not drawing too much current through this, then these things won't overheat because you'll have to dissipate whatever the input voltage is minus the output voltage. That amount of voltage is getting dropped through this component. And so let's say the input here is 17 volts and your output is 9 volts. You're dropping 8 volts across here. And if you're drawing 1 amp through this, 8 volts at 1 amp is 8 watts. So this component will have to dissipate 8 watts of heat. Right? So as long as you're not drawing too much current here, it won't have to dissipate too much. It'll be fine. Yeah, so Jeff, you're probably right. It probably would work at 240 volts. I wouldn't recommend it. Swap out this transformer and you'll be fine. Nerd Garage says, listening to Mark explain just about anything is always educational and fun. Thank you very much, Nerd Garage. And now you know why those pieces have heatsink mounts. Yes, TO220s. And I'm drawing under my head again. Let's take a look at what those look like. So the footprint for this package, where is it? Package, there it is. TO through hole, TO220, TO220. So there we go. So this is what the TO220 looks like. I mean, you've seen these everywhere. This is a very common transistor package. It's called a TO220. TO stands for transistor outline. This happens to be the 220th transistor outline that they created. I don't know where that number actually comes from, but that's what a TO220 looks like. And then if you heat sink, they come in all shapes and sizes. Like, you know, really big ones, or little tiny ones, you know, depending on how much heat you need to be able to dissipate. And on some applications, you don't even need to put heat sinks on them at all. You can, the metal tab on the device will just be enough.
That was actually what I was going to ask. I swear I've seen those on some application where they were just, the metal tab was sitting against a metal chassis.
Oh yeah, if the metal tab is screwed to the chassis, that's even better because the chassis is a large surface area, right? You want something that is a large thermal mass that will draw the heat away from the component, and then something that can radiate it away. That's what the heat sinks are for. The heat sinks don't make it colder; they just make it easier for the heat to get away from it, right? And so a case will do it. And if it's not generating a lot of heat, then the little metal tab that comes on the component itself is oftentimes enough. You don't need to add any additional heat sinking. Cool. Yeah. Okay. We're going to get out of this. Do you have any other questions, or should we start wrapping up?
I can't think of anything else. I really appreciate you covering all the questions I've had.
Oh, you're absolutely welcome. Are there any other follow-up questions in the chat room? I do want to thank the chat room for joining us tonight. This is, I need to get into doing more live streams. And as Halibut Electronics, a lot of my products are proprietary, and I don't want to live stream the work I do on those. I am doing some open source projects now with OHIS, and I have been live streaming that, but I don't know that that's going to be enough to do that. I kind of want to start doing these where I showcase projects from other people and maybe help them figure out some of the problems or the next step or whatever it is. Is that something that would interest you? Please let me know in the comments below, or if you're in the chat room, put it in the chat. That is something that I would like to start doing. Ben, thank you very much for coming on. I love what you did with your projects. I'll be honest with you. That case, the heat shrink tubing case that you used as the case for your first version, I think I like that one better than the 3D printed one, just because it shows the spirit of the project. I think it really fits well with the spirit. So your 3D printed case was rad too. Don't get me wrong.
Thank you. I appreciate it. The heat shrink case definitely had a lot of character. Yes,
it did. Okay, what I'm going to do is I'm going to save these files and I will email them to you so that you have them available. I can help you get KiCad set up, or I'll also include PDFs of them so that you can just view it and use it for your own reference. You're absolutely welcome to follow up with me either in Discord or an email. If you have a lot of work, like if you would say, you know what, Mark, you've convinced me, let's go learn KiCad and let's lay this out on a circuit board, then what I would do is I would start up a live stream and I would have you drive and share your screen, and I would help you out in KiCad if you wanted to do that. I've already put you on the spot. Sorry about that. I'm not going to put you on the spot and say you have to do this or ask you to do this on the call. If you decide that is something you want to learn and are willing to live stream it, let's do that. But otherwise, yeah. Thank you very much, Ben.
Hey, thank you. I'll definitely get back to you on that if and when I get to a point that I want to, learn KiCad and also lay this out on a board.
Yeah, absolutely. All right. Thanks, everybody, for joining us. We're going to go ahead and wrap it up now. I've been babbling enough. You can reach me on Mastodon at smitty@halibut.com or email mark@halibut.com. I've always been hesitant to give that out, but if you've made it this far in the video, I'm assuming you're not going to come hunt me down and spam me. Ben, if people wanted to get a hold of you, what's the best place for them to reach you?
For this audience, I'd probably say I'm on the Ham Radio Workbench Discord, or I'm available at KN4RFT@gmail.
All right, there you go. Yeah, let's go ahead and throw a link to the Discord in there. Actually, the link to the Discord is hard. Go to hamradioworkbench.com. There's a link on the webpage there if you want to join us on the Discord there. All right, we're going to wrap it up now. Thank you so much, Ben. And yeah, say your goodbyes, and we'll QRT.
Thank you, Mark, and I want to say thank you to everybody who joined us in the chat tonight.
Thank you very much, Peanut Gallery. Be good humans.
Bye.
And then I'm going to wait for that wave to come through the stream before I click stop streaming. So